Let's solve the question. Express 729 as a power of 3. To solve this, we'll break down 729 by repeatedly dividing by 3 until we reach 1. Let's start with 729. When we divide by 3, we get 243. Dividing 243 by 3 gives us 81. 81 divided by 3 is 27. 27 divided by 3 is 9. 9 divided by 3 is 3. And finally, 3 divided by 3 is 1. Now let's count how many times we divided by 3. We divided by 3 6 times to get from 729 to 1. Therefore, 729 must be 3 to the 6th power. Let's verify our answer by calculating 3 to the 6th power. 3 to the 6th means multiplying 3 by itself 6 times. 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243, and finally times 3 is 729. This confirms that 729 is indeed equal to 3 to the 6th power. Let's solve this step by step. We need to express 432 as a product of prime factors. To find the prime factorization, we'll divide 432 by the smallest prime number that divides into it evenly and continue this process until we can't divide any further. Let's begin with 432. First, let's divide by 2 since 432 is even. 432 divided by 2 equals 216. 216 is still even, so let's divide by 2 again. 216 divided by 2 equals 108. 108 is still even, so we'll divide by 2 once more. 108 divided by 2 equals 54. 54 is even, so we'll divide by 2 again. 54 divided by 2 equals 27. 27 is not divisible by 2, but it is divisible by 3. 27 divided by 3 equals 9. 9 is also divisible by 3. 9 divided by 3 equals 3. Finally, 3 is divisible by 3. 3 divided by 3 equals 1. And we're done since we've reached 1. Now let's write out our prime factorization. Looking at all our factors, we have 4 2's and 3 3's. Therefore, 432 equals 2 to the 4th power times 3 to the 3rd power. To verify our answer, we can multiply it out. 2 to the 4th power is 16, and 3 to the 3rd power is 27. 16 times 27 equals 432, and that's how we express 432 as a product of prime factors. Let's solve the problem of finding the value of -1 raised to the 55th power. To solve this, let's first understand the pattern of powers of -1. When we raise -1 to different powers, we get an alternating pattern between -1 and +1. Let's visualize this pattern on a number line. When we raise -1 to an odd power, we get -1. When we raise -1 to an even power, we get +1. So, to find -1 to the 55th power, we just need to determine if 55 is odd or even. Since 55 can be written as 54 plus 1, and 54 is even, 55 must be odd. Therefore, since 55 is odd, -1 to the 55th power equals -1. We can verify this by remembering that any odd power of -1 will always equal -1. To summarize, we use the pattern of powers of -1 alternating between -1 and 1, recognize that 55 is odd, and therefore concluded that -1 to the 55th power equals -1. Let's solve the problem of finding 2 to the 8th power. 2 to the 8th means we multiply 2 by itself 8 times. Let's solve this step by step. First, let's multiply the first 2 2's. 2 times 2 equals 4. Now we have 4 times 2 times 2 times 2 times 2 times 2 times 2. Let's multiply 4 times 2. That gives us 8. Now we have 8 times 2 times 2 times 2 times 2 times 2. 8 times 2 is 16. Now we have 16 times 2 times 2 times 2 times 2. 16 times 2 is 32. Now we have 32 times 2 times 2 times 2. 32 times 2 is 64. Now we have 64 times 2 times 2. 64 times 2 is 128. Now we have 128 times 2. Finally, 128 times 2 equals 256. Therefore, 2 to the 8th power equals 256. Let's visualize this another way. Each time we multiply by 2, we double our previous number. Starting with 2, we double it 8 times to reach 256. Welcome. Today we'll solve a problem involving exponents. Let's simplify and write in exponential form. -4 to the 100th power times -4 to the 20th power. Let's recall the rule for multiplying terms with the same base. When multiplying powers with the same base, we keep the base and add the exponents. Let's apply this rule to our problem. We can see that both terms have the same base of -4. Therefore, we keep -4 as our base and add the exponents 100 plus 20. 100 plus 20 equals 120. So our final answer is -4 to the 120th power. Let's verify why this makes sense. When we multiply -4 to the 100th power by -4 to the 20th power, we're essentially multiplying -4 by itself 100 times, and then multiplying that result by -4 20 more times. This gives us -4 multiplied by itself a total of 120 times, which is exactly what our answer shows. -4 to the 120th power. In summary, when multiplying powers with the same base, we keep the base and add the exponents. This allowed us to simplify -4 to the 100th power times -4 to the 20th power to -4 to the 120th power. Let's solve this problem step by step. We need to find the value of 3 raised to the 0 power. To understand why any number raised to the 0 power equals 1, let's look at the pattern of powers of 3. Let's start with 3 to the 3rd power and work our way down. 3 to the 3rd power equals 27. 3 to the 2nd power equals 9. 3 to the 1st power equals 3. Let's observe what happens each time we decrease the exponent by 1. When we go from 3 cubed to 3 squared, we divide by 3. 27 divided by 3 equals 9. From 3 squared to 3 to the 1st power, we divide by 3 again. 9 divided by 3 equals 3. Following this pattern, when we go from 3 to the 1st power to 3 to the 0 power, we divide by 3 one more time. 3 divided by 3 equals 1. This is why 3 to the 0 power equals 1. In fact, this is true for any non-zero number. Any number raised to the 0 power equals 1. Let's verify this with a visual representation. When we have 3 to the 1st power, we have one row of 3 objects. When we divide by 3 to get to the 0 power, we're left with exactly 1. Therefore, 3 to the 0 power equals 1. Welcome. Today we'll find the multiplicative inverse of 1/7. The multiplicative inverse of a number is the value that, when multiplied by the original number, gives us 1. For example, the multiplicative inverse of 2 is 1/2 because 2 times 1/2 equals 1. In our case, we need to find a number that, when multiplied by 1/7, equals 1. Here's a helpful trick. For fractions, the multiplicative inverse is simply the reciprocal. We flip the numerator and denominator. So, the multiplicative inverse of 1/7 is 7/1. Or simply 7. Let's verify this is correct by multiplying 1/7 by 7. 1/7 times 7 equals 7/7, which simplifies to 1. Therefore, 7 is indeed the multiplicative inverse of 1/7. To visualize this, imagine dividing a whole into 7 equal parts, giving us 1/7. When we multiply this by 7, we're essentially taking 7 of these 1/7 pieces, which gives us back our whole of 1. To summarize, the multiplicative inverse of a fraction is its reciprocal. For 1/7, we flip the fraction to get 7. We verified this works because 1/7 times 7 equals 1. Let's solve this problem step by step. We need to express 2a to the 4th power in exponential form. Let's start with our expression 2 in parentheses raised to the 4th power. When we have a term in parentheses raised to a power, we can apply the power to each factor inside the parentheses separately. So, this means we can separate our expression into 2 to the 4th power times a to the 4th power. Now, let's calculate 2 to the 4th power. 2 to the 4th is 2 times 2 times 2 times 2, which equals 16. Therefore, our final answer is 16 times a to the 4th power. Let's review what we did. First, we identified that we needed to apply the exponent to each factor separately. Then we calculated 2 to the 4th power, which is 16. Finally, we wrote our answer as 16 times a to the fourth power. Remember, when dealing with expressions in parentheses raised to a power, always apply the power to each factor inside the parentheses. Welcome! Let's solve this problem step by step. We need to find the value of 1 over 3 squared. Let's break this down. The denominator has 3 squared, which means we multiply 3 by itself. 3 times 3 equals 9. Let's visualize what this means. We start with one whole unit and divide it into 9 equal parts. 1/9 represents one of these 9 parts. Therefore, 1 over 3 squared equals 1/9, or approximately 0.111 recurring. To summarize, when we have 1 over a number squared, we first calculate the square of the denominator, then write 1 over that result as our final answer. Let's solve question 10. Express 52 crore or 52 million in standard form. First, let's write out our number. 52 crore, which is written as 52,00,00,000 in Indian notation. To convert to international notation, we'll rewrite it with commas every 3 digits from the right. To write this in standard form, we need to express it as a number between 1 and 10 multiplied by a power of 10. Let's count the number of places we need to move the decimal point to get a number between 1 and 10. Starting from 5.2, we need to move the decimal point 7 places to the right to get back to our original number. Therefore, our number in standard form will be 5.2 times 10 to the power of 7. Let's verify our answer. 5.2 times 10 to the power of 7 means 5.2 multiplied by 1 followed by 7 zeros, which gives us back our original number, 52 million. In summary, we've converted 52 crore from Indian notation to international notation and then expressed it in standard form as 5.2 times 10 to the power of 7. Welcome! Today we'll solve a unit conversion problem, finding the equivalent of 1 micron in meters. First, let's understand what a micron is. A micron, also known as a micrometer, uses the prefix micro, which means 1/millionth or 10 to the -6th power. The symbol for micron is the Greek letter mu. Let's visualize this conversion using a number line. The meter is our base unit, and we'll show how microns relate to meters on this scale. 1 micron is much smaller than a meter. It's 1/millionth of a meter. Let's write out our conversion mathematically. We start with 1 micron, which we can write as 1 mu. Since micro means 10 to the -6, we can write this as 1 times 10 to the -6 meters. To put this in perspective, let's look at some real-world examples of things measured in microns. A human hair is about 75 microns in diameter. A red blood cell is about 7 microns in diameter, and bacteria can range from 0.2 to 2 microns in size. So, to summarize, 1 micron is equal to 1 times 10 to the -6 meters, or 0.000001 meters. This is an extremely small measurement, commonly used in microscopic measurements and precision engineering. Remember, whenever you see measurements in microns, you can quickly convert to meters by multiplying by 10 to the -6. This is particularly useful in fields like biology, materials science, and engineering where precise measurements at very small scales are important. Let's solve a problem about expressing the distance between the Earth and Moon in scientific notation or exponential form. The approximate distance from Earth to the Moon is 384,467,000 meters. Let's write this out numerically first. Let's visualize this with the Earth and Moon. Here's the Earth and here's the Moon with the distance between them. To convert this to scientific notation, we need to move the decimal point until we have a number between 1 and 10, and then multiply by 10 raised to the power that represents how many places we moved the decimal. Since we moved the decimal point 8 places to the left, we multiply 3.84467 by 10 to the 8th power. Therefore, the distance from Earth to the Moon can be expressed as 3.84467 times 10 to the 8th meters in scientific notation. Scientific notation makes it much easier to work with and understand very large numbers like this. It helps us avoid writing out all those zeros and makes calculations much simpler. Remember, this represents the average distance between these two celestial bodies, as the Moon's orbit around Earth is actually elliptical, not circular.